Yeah, so this talk is about ICI models. So this stands for Independence of Causal Influence Models. So it's a topic I started to work on December 2020. Everything started indeed with a very difficult brainstorming session with a group of experts that wanted to add 15 parents to a target node without being able to create latent variables that represent concept and then that you can use for reducing the complexity of the structure. So it was a kind of nightmare. And so I had to come up with a solution live. And the nice thing was that my target, was expressed on a numerical scale. So thanks to that, I thought about using, numerical latent variables. So, and I use a sum and also use divorcing for being able to help them to capture the relationship between these 15 pairs, right? So after this finally successful brainstorming session, I was quite satisfied with myself, as Stefan used to say. And then I continue my research on this topic, and we came out with a very comprehensive BayesiaLab ICI tool, right? So this is what I'm proposing to describe today. So this is because with ICI, what we want to do is we want to represent, a parent-child relationship. So this belongs clearly to the topic of local probabilistic models, right? So I'm going to start by talking about that to describe what you can do in BayesiaLab for representing such probabilistic relationships. And a Bayesian network is made of two parts. So there is a qualitative part that describes the graph, so the nodes, the states, and the links between the nodes. And then we have a quantitative part that quantifies the relationship between the variables, right? And we do that with local probability distributions that are associated with each node. So two scenarios. The first one is that your node is what we call a root node, so a node that does not have any parents. So in that case, it's quite simple. The parameter represents the marginal probability distribution of X. And when you have a parent, at least, you have to define a conditional probability distribution, so a distribution that will really quantify the relationship between the parents and the child. So you are going to have one probability distribution per combination of the states of the parents you have chosen. So in this very simple example, I have X1 that has three parents, sorry. And if we have three parents with binary that are Boolean, if you want, we're going to have 8 combinations. So we have 8 conditional probability distributions to define, all right? So in order to define these local probabilistic models, the first thing we do is we use tables, right? So this is by default what you have in BayesiaLab and in most of the software. And but you can also use tree. I'm going to describe that a little bit further, and also formulas, so deterministic or not. But at the very end, in BayesiaLab, when you use a tree or formula, we are building under the hood, if you want, a conditional probability table. So we always have tables, right? So let's start with the first one, the tabular conditional probability distribution. So here you have one entry, so one row per combination of the parent states. So this is really nice because then you can really represent every possible discrete conditional probability distribution. So you have all the degrees of freedom here. But on the negative side, you have a number of entries that grows exponentially with respect to the number of parents. And you don't have any structure similarity within the conditional probability distribution. So here it's an example with 3 parents again and a child. And here, given that my first parent is a Boolean node, so true, false, then the second one has 4 states and the third one has 3 states, we end up with a conditional probability distribution made of 24 distribution, right? So we have what we can call in statistics an interaction term here for the 3 parents. So this represents 96 probabilities, and at the end of the day, 72 parameters to define, because as you know, the sum of the probabilities is equal to 100. So in that case, we don't necessarily need to quantify severe once we know the probability of known, mild, and moderate, right? Because we know that the sum is equal to 100. So this is the tabular representation. Then we have the deterministic conditional probability distribution, where here, you know, the state of the child is going to be determined without any uncertainty when we know the value of its parents. So this is something that is nice, because then you have only one parameter per combination of the parent states, right? So per row. It's convenient for modeling, you know, what we can call artifacts. So something that you have defined, right? So when there is a deterministic nature, like for example, logical gates in electric circuit, or when you are defining, you know, a latent variable that summarizes a set of variables. So here again, I'm going to show you an example, this one. But before going into this example, at the end of the day, as I said before, we are going to still create a conditional probability distribution that grows exponentially with respect to the number of parents. So in the example below here, you see I have 4 nodes, one per tires, with a car, obviously. And I have a node, so it's my latent variable here, that summarizes 4 nodes. So I'm just counting how many tires are flat, right? So obviously this is deterministic here, and I can just say, well, when all the tires are okay, so I don't have any flat tires, so it's 0. If tire 4 is not okay, so I have 1 flat tire, and so on and so forth. And at the very end, you see here, we have 4 flat tires, right? So here I don't have to define this table. So this is done automatically via this deterministic tab here that you see, right? But again, at the end of the day, when you validate, this is what you have here. You're going to have a probabilistic table, right? Then we have the tree conditional probability distribution. So here we are using a probabilistic tree. So this is useful because you can exploit what we call contextual independency. So in a Bayesian network, we are exploiting conditional independencies. Here we are exploiting contextual independencies. So this is an example here where I have the accident that is defined by the fact that there is a red light running, that the alarm status is okay, and that the alarm is triggered or not. And for this, I can switch to the third tab here, tree, and define this tree. So I'm saying that if there is no red light running, so there is no accident, right? Then if there is a red light running, depending on the alarm status, if it's okay, so the alarm status, if it's triggered, is going to be 80-20. If it's not triggered, it's 10-90. And when the alarm status is not okay, it's 10-90. We don't care about the fact that the alarm is triggered or not, right? So given the alarm status, then alarm is contextually independent, right? For alarm status equal false. And at the end of the day, this is again what we have, right? So we have a conditional probability table that is populated by using this feature, right? So as you can see, we have different ways to populate this table. The last one I want to talk about are the formulas, right? It's even more efficient now. So we have 2 types of formulas. We have the deterministic formulas. So this is a way to, you are going to use an equation for, computing for each parent state combination, what is the output, right? And the output of this equation is going to be the state of the child, right? And for probabilistic formulas, we are applying the formula for each parent-child state combination, so each cell in the CPT, and then the formula returns something, a numerical value that we are, at the very end, normalizing to get a probability distribution, right? So this is an example of the deterministic formula. So again, with my flat tires here, I've just associated 0 with okay and 1 with not okay, right? So this way, I can just use here this equation where I'm just summing, the state values that are associating with the node tier 1, 2, 3, 4, right? And then by using this equation, as I said, for each parent combination, we use this equation to return the state. So here we have 0, 1, 1, 1, and we end up with 4. So very convenient for populating this table. But again, at the very end, we have a conditional probability table. And here, this is an example with probabilistic formulas. So I have here financial losses that depends on fire extinction with the firefighters, with the sprinklers, and with the extinguisher. And here I'm describing, it's a conditional Gaussian here. So depending on the Newman presence, I have two normal distribution, right? So by using this formula, I can generate this distribution, right? And this one is just also, it's a normal distribution where the mean is estimated by using the mean value of these three parents, right? So quite easy to use. And here you have to look at this little number. We can use this equation to populate tables that are made of 4,000 here rows, right? Oh, not rows here, 4,000 cells, more precisely, right? So it's still a huge conditional probability table, right? So the thing is, we have tools for describing this complex conditional probability table, but at the end of the day, what we do with these tables is we are really representing interaction between the pair, right? And so it's super flexible, it's really convenient, because given that we are really, exploiting the fact that a Bayesian network is a non-parametric model. So with that, we have all the degrees of freedom. But, in many cases, the parents have an isolated influence on the child, right? So, and you can see that in brainstorming sessions that it's not that frequent that you have interactions. So the idea is, how can we exploit the fact that the parents are not interacting, right? So we are gonna use here, exploit this independence of causal influence by using some function. And usually this is a deterministic function. And I'm gonna start with a very classical example. This is a logical OR, right? So this is a perfect example for illustrating independence of causal influence. And here, this is just this scenario where I have 10 nodes, 10 causes, so all Boolean, right? And a symptom. And the idea is that we're going to consider that this symptom can be triggered by any of these 10 causes. If we represent all dimension with these Boolean variables, then we agree that given that I have 10 parents, I'm going to end up with 2,048 cells, right? But the thing is, let's assume that, for example, one cause for sure will trigger the symptom. So this means that if there is only one that is true, then the symptom is true, and I don't care about the status of the other causes. So in that case, using these 2,000 cells, it's useless, right? I just need to know if there is at least one that is true. So with that, we can, once you know that, so just the definition of an OR, so I can use my formula and then write the equation that describes this logical OR. So I'm quite happy because in a few seconds it's done, right? But still, it's done, but I'm using a table of 2,048 cells, right? So instead of using that, because it's quite expensive in terms of memory, I'm going to try to use what we call divorcing. So divorcing, this is when your function, so here's the OR function, is associative and commutative. So then in that case, we can decompose this conditional probability distribution with this kind of graph. So here, what I'm doing is, instead of having a final OR that is using the 10 parents, I'm first computing an OR between the first two causes. And then I'm computing a second OR by using the first one and the third cause, and so on and so forth, right? So by using divorcing, I'm reducing the representation of this conditional probability distribution. And then now I just need to represent 72 probability distribution. right? So it's a huge reduction. Then you have the example of the noisy OR. So the noisy OR, and here I'm going to start with what we call the mechanistic network of this noisy OR. So now we are going to assume that the causes are no longer deterministic. It means that when they are true, we are not sure they're going to trigger the symptom, right? So for that, we are going to associate what we call a causal mechanism that will modulate the effect of the symptom here. And this is done via this kind of network. So I'm still here have my 10 causes, right? And I have one mechanism per cause, right? Which is here Boolean. And this mechanism will really define when this cause is going to be expressed, if you will, right? So in this example, for example, I need for effect one to be true, I need to have at the same time cause one and mechanism one true. If they are true at the same time, then the symptoms or the effect of cause one is going to be triggered, if you will. And given that I have an OR after that, this means that the symptom is going to be triggered, right? So this is a way to have a noisy OR by using divorcing and by representing explicitly here the mechanistic network, which is a causal mechanism. So we can also use what we call the mechanistic network. So this is coming from the Heterman work in the 80s or 90s. And here the idea is just because usually it's not that easy to have access to the mechanisms that express why the symptom is going to be triggered. For example, you have your second shot for the vaccine for COVID. For some people, it's going to have fever, and for some, you don't have fever. So there is a hidden mechanism here. So instead of representing directly this mechanism, we are going to just represent a local effect. That's going to be the effect, but by taking uncertainty, by directly managing the uncertainty associated with the cause one. So here it's like digesting the mechanism inside this local effect. It's going to be false for the OR, and when it's true, then 70% of change that the symptom is going to be triggered, right? So this is my mechanistic network for the noisy OR. And then when you use this kind of network, the question we ask to the expert is, what would be the probabilities that cause one here triggers the symptoms if it were the only cause, right? So you don't have these 2,000 questions to ask, but just here in that case, 10 questions, right? One per cause. And usually what we do is we add what we call a leak node. So this is this node, and this leak is here for representing all the other causes that are not explicitly represented in your model. Here I take into account 10 causes, but perhaps there are 5 or 10 other causes that I don't know really lots of things about them, or their prior is super low, so it's not really worthwhile to explicitly represent them. So we can just take them into account via this leak node, right? And then so this is at the end of the day the leaky noisy OR model, and this is the version you can have without divorcing, right? So you can use, there is an equation in the formula editor, so you can use a noisy OR here and define what is the probability associated with the leak, and then what are the probabilities associated with all these causes. So this is going to be exactly the same thing as this one, except that, again, we are going to use this formula for populating a table of 2,048 cells, right? So now I want to talk about symmetric ICI models. So in that case, we don't have any constraints on the type of node that represents the parent. So in my first example with the noisy OR and the OR, all the parents were Boolean. And then I was using an OR for computing the probability of the symptom. In this symmetric ICM model, we don't have any constraint for that. The only thing, it's not really a constraint, but this is something that is nice to have, is to have what we call a neutral state, right? So when you use a Boolean variable, in the example of the causes and the symptoms, the neutral state is false. So if there is no cause, indeed there is no effect. So we are usually trying to have such a neutral state. And then we have local effects here. So we have a layer for representing the local effect. So this is the same thing as the mechanistic model I was describing with the noisy error, right? And we have a function that will combine this local effect into an overall effect here. And this overall effect, well, the function is deterministic, associative, and commutative. So, which means that we can use the OR that I've just described before. We can use N, we can use mean, we can use max, we can use the sum, right? And thanks to this, the fact that the functions are associative and commutative, we can easily, divorce these nodes, and then we can reduce the size of the representation of the conditional probability distribution. So this will improve the inference speed too. Right? And then we have a last layer that will make the connection between your overall effect and your child. Right? So as you can see in this example, I have parents where the first one has 4 states. It's no A, B, C. Then this one is -1, 0, 1. This one is false true. This one is lower, this one higher. And my child here is true, false. And I'm going through, so my local effects are expressed as integers here. So this one is 0, 1, 2. This one is 0, 1. This one is 0, 1. This one is -1, 0, or 1. So we have positive effect or negative effect. And in this example, this is even reversed, because when you increase, you are increasing the risk. So it's better to be negative. So the reason why it's in green here. And so all these local effects are then summed here. So I have this effect here that is a sum of these two. And then at the very end, I have a final node that sum all these local effects. And I'm using a threshold function here that will map this overall effect into a binary node, right? And as you can see, this is usually, so either it's a pure threshold, so a deterministic threshold, above which you're gonna decide it's true or it's false, right? So it can be, for example, when it's positive, it's gonna be true. Otherwise, it's negative, it's false. But it can be also a smooth threshold, and you can, for example, use a logistic function for that, right? And in this example, what the question we asked to the expert are, what would be the effect of cause 1 on the overall effect if it were the only cause, or all the other causes were in their neutral state? So this is the reason why it's always cool to have a neutral state, because the question is much easier. Right? So the only thing that is sometimes not that easy is that the experts have to understand this transition, this function, right? Because they know this, they know that, but this is kind of internal machinery, and sometimes you have to explain how you're going to convert this overall effect into the states of the child. So if you are interested in modeling interaction between parents, because in the other example, or each parent have really an independent impact on the target, you can here define joint local effects, right? So in this example, I have the equivalent of an interaction term here. So I'm using cause 1 and 5 and 6, sorry, to create a local effect that merge these two causes, right? So here I'm going to have the interaction between these two causes plus the other one, all right? Then I told you that the combination function usually is deterministic, but it can also be a decomposable probabilistic function. So an example is a noisy vote here. So the noisy vote here, we are indeed counting. So my target here, or my child, has 3 states: low, normal, and high. I still have my different causes with different states that are not compatible with the state of my child. So this is the reason why I create local effect, not just for, representing the uncertainty, but also to have a mapping with the state of my child. And then we just count here. So you see with this equation, in that case, for effect C1 and effect C2, for this one, when both are low, so I have 100% for low. When there is one low, one normal, it's 50-50. When I have one low, one high, it's 50, 0, 50, right? So we're just counting here. And at the very end here, given that we are using all these ones, it's you have to remember how many causes you already processed. So for example, this one, I have low, but it's low coming from this node that is taking into account already 4 different causes, right? So in that case, it's going to be, the weight of this one is going to be 4. So reason why you have 80-20, right? So this is a noisy vote, which is very useful for some applications. Then we can have also what we call a weighted noisy vote, right? So here just use function nodes, and then with this function node, or you can also use constant if you want, you're going to be able to associate a different weight with each node, right? So this is kind of the theory. Now I'm going to switch to the implementation of these ICI models in BayesiaLab. And I'm going to do as I did on Monday. I'm going to start with videos. It's easier. And here I'm starting by creating, so I have this network. I have the 6 causes I've already used. I select, here I'm going to connect first my target or my child with all the other one, because at the end of the day, this is what we want to represent, right? So we have these 6 causes, and we want to quantify the relationship, the impact of these 6 causes on symptoms, right? But if I do that, I'm going to have a conditional probability table made of here 288 combinations. So if I were to do that during a brainstorming session, this means 288 questions, and you have to think about at least 1 minute per question, right? When they are efficient. So which means that this is something you want to avoid, right? So now I'm deleting all arts, and then I have just to select the node I want to use for my ICI. I go to Tools, then Independence of Causal Influence, and here I have the node I've selected are here. I just have to define what is the node that is a child, if you want. What is the output of this ICI model generator? So here, given that it has been sorted by the alphabetic order, I'm lucky. Symptom is the last one, so it's checked. And then I can select what is a combination function I'm going to use, right? I can also choose if I want to use a mechanistic local effect, if I want to use a leak node, if I want to have a tree-based decomposition or chain-based decomposition, even though you don't really care about these 2 last options. And here you have the combination function you can use, right? So I'm starting with the OR, and with that, you see, even though I did not select a mechanistic local effect, I have 3 local effects, right? So 1 for cause 1, 1 for cause 2, and 1 for cause 4. This is because these 3 nodes are not Boolean. So if I want to use an OR, I need to have these local effects, right? So the thing with the option to use a mechanistic local effect is that if you check this option, you're going to have local effect for all nodes. If you don't check that option, we are just going to create local effect when the domain of the node is not compatible with the child domain or with the combination function. Sorry. So code 3, it's okay. 5 and 6, it's okay. So when you have this network that is generated, obviously the local effects, the tables are empty. So this is something you have to populate with your experts. But for the logical nodes, obviously, you have formulas, so everything has already been populated. So you have these logical ORs that have been implemented in these nodes, right? So the only thing that you have to do is to define the conditional probability distribution associated with the local effects. Now let's open another network where I have already defined these local effects, at least for cause 1, 2, and 4. So here you can see that my neutral state is no for cause 1, so I'm setting 100% for false. And then I've defined here it's a 20, 40, 80 for ABC. You can think about that as a risk level, if you will. For cause 2, I have other, so 1 is my neutral state, and 2 and 3 are risk level 2. And here you have the neutral state is designed. When it's lower, the risk is lower than when it's higher, right? Now, I'm selecting these 3 local effects plus my 3 causes using my ICI model generator. I'm still using the OR function. I do not check here a mechanistic local effect. And given that now the nodes that I've selected are all compatible with the domain of my child, I don't have to create any additional nodes, right? So now they are all compatible. And now, given that I had quantified already my local effect and the probability distribution for the other causes, I have a fully specified Bayesian network, right? Which is not really noisy, or it's in between, because you have this local effect for some, and for some causes, it's not noisy, right? Now I'm deleting these 4 nodes, and just to illustrate that I can do obviously the same thing with an AND, right? So I'm going to the ICI model generator, select AND, and now it's a kind of noisy AND. Right? So if I said that symptom is true, then you have the posterior on all the causes, right? And the last one is about, not the last one, the third one, by using vote. So same thing, my states are compatible. So I'm not going to create any local effects, additional local effects, right? So if I click on vote 1, I'm going to see that we have the formula that is defined. We have this 50-50 when the effect disagree, if you want, and 100% when they agree. And this one is combining all my causes. Same thing, setting evidence on symptoms to see the conditional probability distribution of these causes. And the last example is with the sum. So obviously the sum, I'm going to have to create local effect because my nodes are not compatible, except perhaps cause 2, but I don't want to use it directly. So I'm going to, I'm checking this option. And then so I have a local effect associated with all causes, right? And here we have from -1 to 1, so -1, 0, and 1. So this is because symptom has 2 states. So we have this -1 for being able to represent negative effect, and +1 for representing positive effect, right? Obviously, during the brainstorming session, you can also decide that no, this node does not have any negative effect, so you can delete these states, right? But this is what we do by default. And here we have, so it's not really a logistic function, but it's something that is close to that. It's slightly more, the slope is harder if you want, but it's better for prediction, right? So you see this smooth, so we have when it's 0 here, you have really the 50-50, and then when it's negative, it's going toward false, and when it's positive, it's going toward true. So this was the first example. Now I'm going to show you the utilization with the B key. So I'm kind of simulating a brainstorming session here. So I'm importing my experts. So I have a dictionary for my expert. I open my interactive session. And now, so I'm gonna select my nodes, then ICI, I'm using the noisier with a mechanistic local effect, plus a leak. And then I have this question. So what would be the effect of cause one on the overall effect if it were the only cause, right? So this is what I have to ask to the experts. So I go here, I can already populate this cell because I know that this is a neutral state. So I don't have to ask this question to my experts. I just have to ask A, B, and C. So what is a probability that is associated with A, B, and C? So I'm selecting these three cells, those three questions, and then I just send that to the BT server. Then my expert, John Doe, here is going to answer that. So you see, this is the first state of cause one. I have the questions that correspond to this, well, the fully written question that correspond to this probability distribution. The expert can use a slider to define the distribution, use a confidence level, and then once it's done for the three states, everything is sent to the BayesiaLab server, and then BayesiaLab will be able to retrieve these probabilities. And here you see for A, I have the distribution, B and C with a comment and so on. Right, so this is the only thing we have to do during a brainstorming session with this kind of model. So I have to do that obviously for all my causes. Now I want to show you another feature that is directly connected with parameter updating. So the idea is you have to imagine that we have a fully specified model that we have designed by using this ICI approach. And for some reason, we want to go back to the conditional probability table where all parents are directly connected to the node, right? So here I have my fully specified table. So for effect one, so I have that for all my nodes. You see my neutral state. If I just want to show you two results. So if I set C and 3, then symptom is going to be, the probability that symptom is true is 90%, right? So this is what we have here. And now what I'm going to do is I'm going to generate exhaustive scenarios. So this is a feature I'll talk about on Monday. So here, if you go to evidence scenario file, I'm going to generate the scenarios that correspond to all the combination of the causes, right? And the output is obviously my symptoms. I have 288 scenarios. So one scenario at the end of the day is going to be one row of my conditional probability table. So I have now my scenarios that are associated with my network. If I make a click on this, I have the list of these evidence, right? And now if I go to evidence automatic evidence settings, I can see that I have hard evidence for the states, for the causes, right? And probabilistic evidence for the child. And I'm going to use that. So now I'm deleting all these nodes, connect symptoms, set symptom as a child of all these nodes, right? And now select symptom, go to inference, parameter updating, use as evidence source my evidence scenario file with my 288 scenarios. The node that I have selected is just symptom, and I just want to use this one because then I'm going to initialize the prior weight to 1 and the discount to 0. So discount 0 means that I'm not going to use any directly prior here. And with that, I'm going to be able to build the conditional probability table here automatically, right? So now I've learned my table, so I can go back. And if I go back to modeling, I even don't go there, I can show you that with C and 3, we have the same posterior probability distribution for symptom, right? And you have this table that has been automatically populated via this parameter updating. So this is a way to go back to these tables. This is sometimes useful for reducing the size of the network. So it's purely for communication purposes, because sometimes when you use ICI, so you are reducing the complexity, but by adding nodes. So at the end of the day, sometimes it can be a large network. So sometimes for just having something more compact, we can use this feature. And the last thing I want to show you is the feature we call the multi-restart parameter updating, so that I have described quickly on Monday. And here, so it's a mix between multi-restart parameter updating and ICI model. And I'm going to show you that in the framework of supervised learning. So now we are not talking about expert anymore, but more about machine learning. I have a data source, one of my favorite data sources here with the US Army guys. So I have a learning test indicator. I have 507 soldiers here that are described by their, elbow, chest, and so on. 50% of the data set is used for learning, 50% for testing. And my target node is going to be weight. So I want to predict the weight of these soldiers by using the metrics of their body, right? So given that this is my target and this target is continuous, I need first to discretize it. I go then into manual. Then, given that I don't know how to discretize it, I don't have any threshold in mind. So I'm just going to use R-squared GenOp 5 for finding the best threshold. So the threshold that best represents this density function. So I have these 5 thresholds. So now my target node, as you can see, the color is slightly different. So it's not turquoise anymore. It's a bluish here. So which means that it's manually discretized. And then I'm going to be able to use this node as a target for my bivariate discretization algorithm. So all the other variables, I'm going to discretize them with the tree, right? So tree by using weight as a target. So I'm setting 5 intervals because you remember that tree we are using for that is based on an MDL score. So I don't care about the number of intervals because the MDL score is going to will take care of the number of beams, right? So I just finish. Then here I have a warning because it seems that age is not correlated enough with weight. So I have to choose another discretization algorithm. Here I'm going to go back to R-squared GenOp star 5. So same thing with the R-squared GenOp star. We are reducing, if needed, the number of beams. I'm excluding BMI because otherwise it's going to be too easy to predict weights, right? And I'm setting just weight as my target node. And I'm starting with, our usual augmented markup blanket. This algorithm will find the nodes that are here directly connected. So it looks like a naive, but it's an augmented markup blanket, or at least obtained with a markup blanket algorithm. As you can see here, I had a warning because for when I'm trying to build the confusion matrix for some combination, the algorithm cannot take a decision because I have a uniform disruption. So it's either uniform or impossible. And in that case, it's just impossible. So we are going to see how we can solve this problem. So here we have, given that I want to use this network for predicting weight, the metric I have to look at is really the R-square, because this is really, I'm focusing on the continuous value, even though I can have a look at the precision that is 75% here. Everything on the test sample here. So 87 for the test sample, 93 on the learning. And then here, the new feature I show you on Monday, the scatter plot that shows you the predicted value on the y-axis and the actual value on the x-axis. And as you can see, because of the discretization, you have this kind of strange scatter plot here. The R-square is good, but it's a scatter plot by, where you clearly see the beams, right? And so in order to prevent the the impossible combination here, the solution is to use a directly prior to set a non-informative prior. So we just do that by using the classical smooth probability estimation. We just add like one virtual soldier that is spread uniformly across the joint probability distribution. We use a Markov blanket learning. We switch to validation, do the performance analysis, and now we have a performance of 0.88 for the R square, right? So slightly better, and 94 for the learning sample. Scatter plot, more or less the same. So this is by using the augmented Markov blanket. So now what I want to do is I want to use my ICI model to see if I can do something different, right? So I'm keeping this, I don't know, 2, 4, 6, 7, 9 children, and I'm gonna exclude all the other ones. Right. So indeed, here I'm just using the augmented Markov blanket for selecting the nodes, right? Then I'm gonna just here select all nodes and use my ICI model generator using the sum. So I'm checking a mechanistic local effect, then the sum as my combination, and set weight as my target, but it's already done. So this is the output by default. So all the pink nodes are already populated. So I have my deterministic function that just makes the sum of all these local effects. And I just have to populate, the local effects. So I have 9 local effects to populate. And if I double click on the first one, you see I have this table. So given that my weight has 5 states, we are going from -4 to +4. So just to be able to capture, again, negative and positive effect, but be able to not just -1 and +1, because we have these 5 different states. And here, I'm not going to ask the expert to populate this table, but rather, I'm going to use the data for automatically populating these tables. Right, so I'm selecting, so here this is just a transition function between the overall effect and weight. Here, this is a sum. And I'm switching to validation, selecting my 9 local effects, then multi-restart parameter updating. So this will allow me to randomly generate distribution for all these effects, and then use expectation maximization for trying to minimize the entropy of the data given this model, right? So I'm setting always a huge number of iterations. This way I have kind of anytime algorithm that I can stop when I'm okay. Then I'm just gonna use the learning sample for the estimation. And here in the console, you are going to be able to see how the score is evolving. So the first entry is 15.91, and so on and so forth. So you see here, obviously I have a little bit accelerated time because it can be time consuming with this huge sum node. And then, so I go to the network performance target, and do the same thing as what I've done with the augmented markup blanket. And I have here an R square of 0.9. So if you remember, the other one was 0.88. The precision was 76, I think. Now it's 78. And what is quite interesting is to see the scatter plot. That is much nicer than with the augmented markup blanket. And also the calibration index that is 78 in this case. And here are the tables, the local effects that have been estimating via expectation maximization. Right, so here it's like a logistic regression model, or regression model, if you will, where we don't care about linearity and so on, because at the end of the day, thanks to the local effect, we can handle nonlinearity. And so this is, I think, quite interesting. So this was my last slide. So I see that I'm just a little bit late, but